I want people to ask questions as they go. Make sure I've got a red. I need this black because it sticks out like dog's balls. Can I see it there? Okay. Where are you, Mick?
It's going.
What we're going to do is I'm going to explain the concept of a high impedance neutral. The concept. So, tell me yes or no. Does this look like a typical transformer connected to earth? Current flows, voltage doesn't flow, just in case you forgot. Voltage doesn't flow, current flows. Current flows through here, through the active here. I've put in here an RCD. I've forgotten about the main switch, and for the sake of this exercise, I've just put in an MCB RCD. Over here down into a load, I've given that 10 ohms, just an easy number. Return path on the neutral up to the neutral bar. And MEN link over here, earth connected down to the earth stake. I've given the earth 50 ohms in between our earth stake and the earth stake at the transformer, or it's MEN at the transformer. And for the sake of numbers, Fitzy, I've put in 0.01 ohms on the neutral. If I wanted to be really fair, I would put in like an impedance on this, and I'd put an impedance on this, but just to make the numbers work and to make this simple, you can get the concept, no worries, with just having 0.01 of an ohm on the neutral. So why is it that we don't get a shock when I touch the earth? And I'll ask you a question. Do I get a shock if I touch the earth at the moment?
No.
No. Why not?
No current flow on
Very, very small current flow on the earth, and basically there's no real potential between the earth bar and the ground. So we'll prove that in a series parallel circuit. So supply, which is transformer. Over here, do we say, is that our 10 ohm load? Do we bump into 0.01 of an ohm for our neutral?
Yeah.
And we return. Do I have to add anything else to this circuit?
50 ohms on the earth.
The 50 ohms parallel with the 0.01. Now you have to remember that just because it doesn't look like it's parallel, this 50 ohms is parallel with the 0.01. So it might not look like it when you straight look at it there, but if you think about it, Harvey, after the 10 ohms here, you think about the point, after the 10 ohms here, we're at here. Now the current can get back from here, this way, 0.01, or this way via the 50. So the 0.01 and the 50 are in parallel. Now, if I'm here, Dill, let's just say, here's Matt, and I touch something here, I would be creating another path back to, potentially I'd be creating another path. Current here, over there, or through me. So if I wanted to be, I'm not going to do it, I'd put myself in here. I'm trying to emphasise the point that the voltage in between here and earth is what I'm concerned about. And for the smart guys in the class, they would say that my math is not quite perfect here. We're assuming that in between here, if I could reach my foot all the way over to here. So I'm putting myself in parallel over here. Obviously, depending on where I stand, would affect the touch voltage, but we're going to take the worst case scenario, if anyone caught that. So 10 and 50 and 0.01, I'm going to turn that into 10 and 50 and 0.01. Someone, that one's easy, we just go 0.00 9. Is that right, Hamzy? So I've got a total of 10.009. I've just done the reciprocal on that. 1 over RT equals 1 over 50 plus 1 over 0.01. It gets me to that. So the current in here is what? I'll give you, you need a voltage. So
230 or?
230. So we'll just say 230 the whole time. VP equals 230.
22.9.
22.9 amps. So as far as the voltage goes, we can do volt drop over here and volt drop over here. Volt drop V equals I times R equals, 229 volts. It must be 229 point something, is it? Someone else on the calculator, not just I times R, well, it's not just 22.9, it's 22.9 something. I want all the decimals to make a
All
point.
the decimals?
Yeah, sorry, I want to make a point. 230 divided by 10.009.
22.979.
Okay, amps. Just to make a point, I'm going to that extreme here. And the volt drop over here is 229.7. Is that right? Pretty sure it is. Someone's good at maths. So therefore the voltage that's over the earth here is V equals 222.97 times 0.09 equals what? 0.3. Is that about right? That will do. Am I close enough? Hamzy, or what?
Yeah, it's not.
Okay. So the voltage that is present here over the earth, the voltage is present in between here and here, or here, or essentially between here and me, between here and the earth, is 0.3 of a volt. Who's got a question about that? Can people see that I'm not going to get a shock? Can people see that if I had a millivolt meter, I'd pick up a very small voltage? Do we want it, for the sake of it, see the current that would be flowing through the MEN link, or flowing through the earth? With this, could I tell the current that's flowing through the earth and the current that's flowing through the neutral?
Yep.
Do I have the ability to do that? I equals V divided by R, which is 0.3 divided by 50. So the current that's flowing through the earth here is what?
0.006.
0.006 of an amp. So I've actually got 0.006 of an amp flowing through here. And the current that's flowing back on the neutral is the rest. So 22.9 something. You got a question about that? Okay. So in this situation here, the installation's completely okay. Is it, you happy with that? There's hardly any touch voltage present, but there is a small voltage present, is there not? There is a very small voltage present. I'm just going to now add, with no fault, so there is no fault, or I won't put a fault in this installation yet, I'll add another load. Let's see what happens when I turn another load on to make a point. You alright? Another 10 ohm load, are we okay with that? So I've just added another 10 ohm load. That would happen in a real life situation, wouldn't it? More loads get turned on in parallel. So can I do this math again? Except I haven't got 10 and 10. Oh, I haven't got just one 10, I've got 10 and I've got 10, have I not? I'm doing this a bit quick, assuming that you obviously passed the LET, so you understand series parallel circuits. So I'm not putting all the math up. I've got 10 and 10 and 0.009. Is that how it looks? So therefore, does it look like this? 5 and 0.009. Yes? So have I answered this question for me, Stouty? By putting an extra load in parallel, have I decreased the overall resistance? Yeah? Okay, I have. So therefore, if I decrease the overall resistance, what happens to the current flow?
It's high.
Goes up. So therefore, I equals 230 divided by 5.009. Someone click on the calculator, come on.
$45.917.
41.917 amps. So let's just check out what happens to the voltage over the load and the voltage over the earth. Let's see if they change. They're going to change, but not by much. So I'm just going to get, so I've got space because I'm not going to take up too much sideways space. So that we're looking at 45.91 amps. So the voltage over the load, I'll change colours, goes V equals 45.91 times 5. What's the voltage over here? $45.91 times 5.
229.55.
So the voltage over the load's dropped a little bit, hasn't it? From 229.7 to 229.5, really not much. And the voltage over the earth has risen to, I don't know, 0.5, 0.45. Dave? Who's got a question? I know the camera's on, but just ask the question. I'm after feedback here. Yeah. I'm about to move on. I'm about to implement a fault in this. Everyone's okay at the moment. So what have I said? What have we seen so far? We've seen that if everything's working fine, I've hardly got any voltage present over the earth. And even when I turn an extra load on and my overall resistance decreases and my current increases, that I have a slightly increased voltage over the earth and a slightly decreased voltage over the load. Is there anything to worry about? What's the minimum, what's the touch voltage limit that I've got to be concerned about? What's the limit of touch voltage? 50 volts AC. Touch voltage has to be kept to less than 50 volts AC. Now, what would happen? We're getting into fault territory now. So this was all without fault. Now, if let's just say that the most obvious example is this, and we said this last week, is an overhead.
Neutral.
Flapping in the breeze. An overhead, fused mains box, wind moving. That's not to say that it couldn't happen in another situation, but that's a common place for it to happen. So if this neutral snapped off or went high impedance, then let's see what happens. We can just put this into a series parallel circuit. So let's just say, Dill, that we went and we saw some high resistance in there of, how many ohms do you want to make it? 20? 20 ohms?
20 sounds good.
20. Okay, so what would 20 be? 20 would be, Dave, let's say, or been a couple of strands broken off, wouldn't it? Over the years, swing round, strand breaks off. Another strand breaks off, strand breaks off. So we've still got a connection. We've got 20 ohms on the neutral. Are we okay? So we haven't got 0.01 anymore, have we? We've got 20. Can I do some maths for that, Fitzy?
Yep.
Okay, let's go. 10 ohm load. I'll forget this 10 ohm load. I won't worry about that at the moment. I'll just deal with one 10 ohm load. 10 ohms. So I go through the load, 10 ohms, I get up to here, And now, I don't have 0.01 anymore, do I? Have I got 20? Yes? 20. Now what's 20 in parallel with?
50.
Is everyone happy with that? That the 20 is in parallel with 50, Benny? Because the 20 is back over here, and in parallel with that is the 50. Let's do the math on that. Fitzy's already doing the math for me.
14.285.
So 10, 14.285, that's what that number is, isn't it, Humsy?
Yep.
So RT is 24.285 ohms. I equals, what's that? Okay, I equals 230. Someone, everyone's just waiting for Harmsy. Harmsy's writing stuff down. Can someone just be completely on the calculator?
9.47.
Thank you. 9.47 amps. So therefore, the voltage that is now over our load, anyone that's one step ahead will see what's going to happen here. The voltage that's over the load here is V equals I times R, 9.47. So I'm looking at 94.7 volts over the load. Someone's going to have to do that, 9.47 times 14 point, it's going to be the rest, which is
135.27.
135.3 volts. So what have we just seen then? We've seen that because I've now got some impedance in the neutral. If I draw it like this, I've got 10 ohms in my load bumping in to what used to be a straight path home, but it's now bumping into 14.285. I'm just making these numbers up. It could be different numbers, doesn't make any difference. So what's that done? We know if we've got a series circuit, that voltage will, dissipate over the two resistors in series. So we've seen, Nick, that I've now dropped 94.7 volts over the load, and the voltage over the earth has risen to 135.3. Is that a dangerous proposition? Have I now, theoretically, if I had this super long voltmeter, which I haven't, if I was in between here and here, I'd be getting 135.3. Now, yes, when you do a test, and if Keogh does a test here, he goes and drives an independent earth. They call it an independent earth. Has anyone ever seen an inspector do that? They drive a stake into the dirt somewhere.
Yeah.
And they use that as their reference point. Why would they do that? Because they can't make it back here. If they could get a clamp on that without travelling over 5 blocks, then they probably would. But they can't. So they just drive an earth stake into an independent earth somewhere. So I've now got a dangerous level of touch voltage present. So what does that mean? Where's current flowing then? So current's flowing through the phase, through here, through the RCD, down through the load, I haven't got that in yet, back through here. Does current flow back up here?
No.
I haven't put a fault in the appliance, have I? I haven't put a fault in the cable, like in the sub-circuit. Up here, up through the RCD. Does the RCD care?
No.
What's going in's going out.
What's going in's going out. RCD doesn't care. So this is bad, isn't it? Usually the RCD saves everyone's life, doesn't it? RCD, amazing device, saves everyone's ass. But it doesn't seem like it's doing it now. Because the RCD just goes, well, the final sub-circuit's all right, that's what it's protecting. What's going in is what's going out. So the current gets to here. Now, previously, for all intents and purposes, all the current went back on the neutral, didn't it? Previously, situation 1. Now what's happening here? Is current flowing over the MEN link?
Yep.
We've got the ability to work out how much current's flowing over the MEN link, and we'll do that in 1 second. So current's flowing over the MEN link here. and down the earth stake and through the earth. And what do you know? I'm dropping 50 volts over it. I'm dropping voltage over the earth, up the earth stake, over here, and I'm back again. There's a complete circuit, isn't it? So I've now got a dangerous touch voltage of 135.3 volts. Do you think it's possible with our series parallel circuit, because it explains everything, to work out how much current's flowing over the MEN link?
Yeah.
You don't have to know that, but I think it's a point. It's an interesting point.
Just got like a current over the.
Because it was previously 0.006. What am I going to do, Hamzy?
Just find the current over the 50 ohms.
Do I find the current over? Yes, I find the current 50 ohms. Yes. I equals V divided by R. So I equals 130. Just go 135.3 divided by 50. I equals 2.706 amps. Well done, I've got 2.7 amps flowing over the MEN link. That's bad news. It's bad news. I've got current flowing the MEN link. I've got current flowing down the earth stake. Well, it's up and down as you know, but for one instant in time, it's down the earth stake. And I've got a touch voltage. So people could get a shock. Who's received a shock in a footy club room shower? Yeah, nothing. We're not going down that path. But why though? Because what they've said, Nick, and it used to happen all the time at certain club rooms, is because all of a sudden you connected to something metallic that's connected to the earthing system. Are you wet? Are you so does water conduct? So there's now the touch voltage that's present. It might not be 135 volts because that gives someone a kick when they're dry, but it might be less than 135. All of a sudden they're wet, so now you're a great conductor. And it just goes, well, go down the earth stake, go down Jenna, go down Matt in the showers, whatever. Okay, I had a shock over the other day. Someone received a nasty belt off a tap. Let's pump this up and let's turn on another load, Dylan, see what happens to our numbers. Are we okay with our numbers? 94.7, we've dropped over our load. So the voltage over our load reduced from 230, pretty much 230, down to 94.7. Who's got a question? Are we all like, I'm sitting there like silent lambs, or are we all just like getting it that clearly?
We're going to do 2 loads here.
We're going to do 2 loads. Hamzy, let's put it on another load. Another tenner, what do you reckon? Another tenner?
Yep.
Just for the sake of it, numbers are 10 and 10 is 5. Okay, so let's put in another load. So I could probably divvy this up over here, couldn't I? So I've got situation 1, without a fault. Just to recap, without a fault. 1 load, without a fault 2 loads. With a fault 1 load. With a fault 2 loads I'm about to go. 10 and 10. Tell me if my series parallel circuit's right, I might be wrong. And 50 and 20. Does that make 5 and 14.28?
285.
Correct. Put some numbers in. I equals 230 divided by 19.285. What's happened to our overall resistance when I put an extra load in? Is the overall resistance reduced?
Yeah.
Has anything reduced over the high impedance neutral or earth? That stayed the same, hasn't it? And it will stay the same. It is what it is.
11.926.
Am I down to 11.926 here?
Yep.
V over the load, I'll go V out 11.926. And V here equals...
Oh no, that's I total.
Oh, sorry, I'm after I. Yeah. I equals 11.926. So here I'm looking at 56, am I? Voltage. I equals V equals I times R. 5 times 11.926.
59.63.
59.6 volts, and the rest is over here, which is someone tell me what it is. It's 60, so it must be 70 something. 170. Is it?
170.4.
130.
170.
So, Paul, when I turn an extra load on, has the voltage decreased over the loads and increased over the earth? It has. And it's just so on and so forth. I could put a third load in here. I'll do two more scenarios. I'll do two more situations. Yeah? Question? Or stretch? Pat? Last. I'm going to put one more load in for the people should be able to see where this is going to go. Another load. 10 ohms. Yeah? Marky, you alright?
Yep.
So I'm now looking at 10 and 10 and 10 and 50 and 20. I'm just going fast now.
Just on that last one, Keith, flowing over the MEN was 3.4 amps.
Thank you, Humsy. So we've pimped this up to 3.4 amps flowing over the MEN link. Got my Humsy just back over here, just did that math there. Okay, 10, 10, 10, 15, 20. That's going to turn into what? That's going to turn into, is that 3.3?
3.333.
Thanks, still. 3.33 and 14.285. Giving us an RT of whatever it is. Someone's going to tell me that. 17.5.
17.615.
615. I equals 230 divided by 17.615. I equals
13.05.
amps. Makes sense that the current's gone up, doesn't it? I just added an extra load. Went from over here, 11.26. I added an extra load, current went up. That makes complete sense, doesn't it? 13.05. Therefore, the voltage over the loads, voltage over the loads equals what? I times R, 13.05 by 3.33. 45.
$43.45.
43.45, and V here equals 187, is it? Point something. Is that right?
186.
Yeah, 186.27. So let's go through the stages here. In a recap, Pat. Over here, you weren't here, you were in Camperdown. Your car broken down. Over here we had no fault, without fault. 10 ohms, one 10 ohm load, 50.01, hardly any current flowing through the MEN link. Hardly any voltage, touch voltage, hardly any potential over there, wouldn't have got a shock, everything's fine. And then over here, I added an extra load, still no fault. Still I had full voltage over the load. And I had still hardly any voltage over the earth. It went up a little bit. Then we got a high impedance neutral. Still had a 10 ohm load, a 50 and a 20. So the 50 and the 20 turned into 14.285. And all of a sudden I saw a reduction in voltage over the load and a increase in voltage over the earth. Why? Because it appeared like I had a high impedance neutral. That can be the only thing, can't it? What could make that happen? The only thing that could make that happen, Fitzy, to make me reduce voltage over the load would be that the current has bumped into another body of resistance that wasn't previously there. That's really it, if you break it down. The only thing that could have happened to make voltage reduce over the load was the fact that the current that was flowing through the load over here bumped into another bit of resistance, substantial bit of resistance, here, and it dropped voltage over that. Where could that be? Well, it's not over the earth. It's not like the earth all of a sudden, like, its resistance went up a whole lot. We've got an earth stake buried deep in the ground, an earth stake buried deep in the ground, so it's not highly unlikely going to be over the earth. So it's highly likely that it is happened in a neutral. Because if it happened in the earth, well, would it make any difference to us anyway? I'll just put the question to you, Stan. You're a smart cat. Right? If it was there, if I had 20 ohms there, and I still had 0.01 there, would I notice any difference?
No, not unless there's a fault on the appliance. Then
Oh yes, yeah. Well, not unless it was a fault in the appliance.
Well,
But-
it still wouldn't because it'd go.
Yeah, because it'd go up here and over here. But the Earth in general, and the Earth stake is just hanging out, doing nothing, waiting for something to go wrong.
If you had,
Yeah.
this might be a bit of a silly question, but if you, let's say you had a impedance in the neutral, then you notice the lights would dim. Would that make the lights brighter, like if it started raining and that? Because the resistance of the Earth would go dim.
So again, if you had an impedance in the neutral
Yeah.
and it rained,
Yeah. Then it rained and would that.
yeah,
make the
with
lights-
increased current. So this would go down, current would oh, hang on, you've got me on a couple of, I have to think about that.
Yeah.
The resistance of the Earth would reduce, so current would go up. Then if current goes, I have to think about it. Well, current would go up over the Earth, but current wouldn't change over the neutral really. But if current has increased and you've got more current flowing through the load, yes, you would definitely. The lights would glow brighter because there's more current flow, so there's less voltage drop over here. So if there's less voltage drop over here, you've got more volts over the load. So yes, theoretically. No, actually. Took me a second to get there, Paul. Now, the last thing you need to know is, or consider, Mick, would be, what happens if the neutral goes completely open circuit? So the neutral's snapped off. Well, I'm pretty sure it's going to be a very similar thing. But let's just do that to finish this off. Now, in the last situation, the neutral's gone open circuit, Nick, right? Oh, we're open circuit on the neutral. I'll just, do you want to just use these numbers here for the 10, 10 and 10? I've still got 3 loads on. 10, 10, 10, so I've got 3.33. I'm jumping some steps so people know what I'm doing. 10, 10, 10, 3.3. Except now I'm not bumping into 14.285, am I?
Don't have a parallel there anymore. It's just.
I don't have a parallel. I'm just bumping into 50. You happy with that? Am I just bumping into 50?
Yeah.
So RT is 53.33. I equals.
4.31.
4.31 amps. And the voltage over the load. Is that right? Yep. V equals I times R, 4.31, 4, 8, 12,
14.35.
14.35 volts. And over here is the rest, which is 200 and